In this video, we're going to take a look at how to prove these standard integral results using substitution. There's sort of two styles of questions that we can get asked on this topic. Like one is to prove where it comes from, and one is just to actually integrate something. And obviously depending on how the question's worded, but if we are asked to specifically prove where it comes from, we've been given a substitution for this first one. We won't necessarily always be given a substitution. After we've done one or two of them, we'll probably have a look at maybe one where the substitution isn't given, but there's a little sort of trick that we can do to help us to decide what substitution to use. So we're aiming to prove that if we integrate this weird looking fraction, say for example, if I was going to integrate the square root of 1 over 9 minus x squared, like if the integral looked like this, we could look at it and say, well, it's in this form, isn't it? It's a squared minus x squared. This integral here is going to become sine inverse. And you might think, well, why do I need this new technique? Like, can't I, I know a lot about integration. Like, can't I just integrate using techniques? Like maybe a substitution would work, or maybe parts, or something. It's a fraction. Is it going to become an ln? And like, if you try and do any sort of substitution, like a natural substitution, like you might say, well, let's let u equal 9 minus x squared. The problem is that, trust me, you can try it. If you do the calculation, it's never going to work. It's never going to cancel out. It's not like, could you do it as a bracket to a power? I mean, no, because look, this function inside, it's not linear, and obviously when we're integrating, if the functions are not linear, it's going to be a substitution, isn't it? But this substitution wouldn't work, and we'll see that actually in general we can do a substitution that will work, but it'd have to be a sine function that we integrate, that we use as the substitution. It's not like your standard sort of substitution questions that you normally get in A-level maths. Okay, so let's just follow the process, like dx by du. If we're saying x equals a sine u, dx by du would equal a cos u. Du divided by a cos u would equal dx. Sorry, it wouldn't be, would it? Dx would equal a cos u times by du. Okay, so we're going to replace this dx with du times by a cos u. Looking inside the integral, we've got 1 over the square root of a squared minus x squared. So x squared would be a squared sine squared. And if I square this, I'd get a squared and I get sine squared. Dx is a cos u times by du. So it looks a bit messy what we've got at the moment, but there's like a common pattern that happens on these substitutions for all the standard results. Like, luckily we do get all these results in the form, luckily we don't need to remember them all. We've just got to like decide which one we're using, obviously if we're going to integrate something, and if we're going to prove something using the substitution, we've got to decide what substitution we're going to use. We need to tidy this up, okay? Looking inside here, the key to doing this right is to notice what we can do inside this square root bracket, okay? If we're trying to square root something, we don't like when there's these two separate terms. Okay, so could I get it as like the square root of something squared? If I could do that, it'd be much easier. I'd be able to simplify it. And the key to doing this for this type of question is to realise, well, we can take an a squared out as a factor, and you're left with 1 minus sine squared. This is a proof question. I'm not going to skip that step. That's a key step now. Would be to write it as a squared times by 1 minus sine squared, which would be cos squared. You might even want to write sine squared plus cos squared, sine squared plus cos squared is equals 1, just to prove this, you're using this identity. And now look what happens. Like, it's actually really neat the way this works out. And you'll know that you've done it right at this point. Like, if I square root this, I get a cos u. So this mad looking thing that we've been asked to integrate, and this really awkward looking substitution that we've done, we end up integrating 1 with respect to q, which just gives me u plus c. And that's the answer. Like, that's where our answers come from. Like, I mean, we're not quite there yet, are we? Like, when we do substitution, the final step is to go back to your substitution. And I know if x equals a sine u, x over a would equal sine u. So sine inverse of x over a is equal to u. Which is what we would have to prove, isn't it? So, like, if the substitution isn't given, which maybe it won't be, because I've seen questions in the past where the substitution isn't given, just look at the answer. Okay, the answer is a sine inverse. The substitution is going to be a sine. If it was like a cosh inverse, the substitution would be cosh. If it was tan inverse, the substitution would be tan. Okay, so we'll maybe try the next one where the substitution isn't given, and we'll just take a second to look at the right hand side and decide what substitution we will use. The pattern is very similar. Like, as soon as you substitute in, because it's a square root of 2 terms being subtracted, the identity allows us to make that into 1 term. It's just about choosing the right substitution so that we get it in the right form that allows us to use the identity. Okay. Example 2 says, use a suitable substitution to prove this result. Okay, so we're going to be doing the integral of 1 over the square root of 9 plus x squared. Probably worth having one idea in the formula booklet. Like, to me, this looks like the integral of 1 over the square root of 9, which is 3 squared plus x squared dx. So I'm thinking about the integral of 1 over the square root of a squared plus x squared dx. Now, clearly, I can't just use the result. Like, the result that's given in the formula, we'd end up just, like, writing the answer down, essentially, wouldn't we? Like, we need to prove this by choosing a substitution. So let's let x equal, we know it's going to be a sine inverse, so we know it's going to be a sine substitution. But it's not just sine, okay? If we try to, just visualize what happens, if you sub sine in here, you'd get 9 plus sine squared. We need to let it equal 3 sine, because if we let it equal 3 sine, when we sub it in here, we'd get 9 plus 9 sine squared. And because they've both got a factor of 9, you can take it out, and then you've got 1 plus sine squared, which allows you to use the identity, doesn't it? And then we can tidy the square root up. So I have one idea on what's going to happen when you decide what your substitution is going to be. Yeah, it helps. Okay, so dx by du would equal 3 cos u. Dx would equal 3 cos u du. And then that would give us 1 over the square root of 9 plus x squared dx, which is 3 cos u du. The identity that we're going to use for this one we know cos squared minus sine squared is equal to 1. So that would allow us to replace this as 9 cos squared. And again, you know you're on the right path when this happens. So we get u plus c. Go back to the substitution. If x equals 3 sine u, x over 3 equals sine u, u equals sine inverse of x over 3. I know I'm doing this in blue, but maybe like it's just because I'm a bit short on space. Like I would actually be, with this being a proof question, I would specifically show this as well, just so you're not jumping from this to the answer, like if the answer is given. Okay. Let's do one more example. It says choose a suitable substitution to show that the integral of 1 over a squared plus x squared is equal to this tan inverse integral. Okay. Sorry, tan inverse. We're going to let x equal a tan u. Again, we can have one eye on the answer. This one is being divided by a as well, but don't worry about that. We'll see in a second what happens there. The main reason why we're going to be doing this is if we substitute in here, that would be a squared, tan squared. Take the a squared out, and you've got 1 plus tan squared. We know 1 plus tan squared is an identity that we can use. We also know that when we differentiate tan, we're going to get sec squared. Okay, so it all sort of very neatly fits together. It's quite nice the way this works. It allows us to integrate these functions by using these inverse tan functions, inverse sine functions. So dx by du equal a sec squared u. Okay, so we sub into our integral. I'm thinking about tidying this up, but I'm also thinking about an identity, like look at what we've got on the bottom. So on the top we've got a sec squared u. On the bottom I've got a squared 1 plus tan squared. Oops. So we know 1 plus tan squared theta is the same as sec squared theta. And that allows us to really neatly tidy this up, doesn't it? Don't forget a is a constant. Don't start doing anything weird with a. A over a squared is 1 over a. Take the constants outside and you're integrating 1 again with respect to u. Okay, so 1 with respect to u would become u. And then we just go back to our substitution to finish it off. So it'll be 1 over a tan inverse of x over a. Thank you.